Hello everyone, I'm Sajjadur Rahman. Today I'm going to present our work on developing Leam, a system designed to enable interactive text analysis. So why are we focusing on text data analysis? Well, the rapid rise of e-commerce in the last few years has contributed to the increase in user-generated text. For example, digital text such as reviews and question answers often contain valuable information. Our research here at Megagon Labs explores problems like question understanding, opinion mining, to name a few. We employ these techniques to extract value from digital text to help enterprises improve their products and services. Therefore, our vision is to develop a system to facilitate workflows for solving these problems and provide a seamless text analysis experience for practitioners. But text analysis is an iterative and nonlinear process involving numerous steps, from project setup and deployment to data exploration. From sharing and collaboration to archival of analysis workflows, recent work has shown that there are many associated challenges. Systems like MLflow, SageMaker, Spliced Machine address the challenges related to project setup, deployment, among others. With Leam, we aim to address various challenges related to data exploration and analysis, as well as sharing of workflows. Leam combines the advantages of computational notebooks, spreadsheets, and visualization tools to enable interactive text analysis. Let's see a motivating example to better characterize the problem domain. Let's assume that a data scientist at an e-commerce company is tasked with analyzing customer reviews of products. To characterize the review corpus better, they would like to perform topic modeling and clustering on the review corpus. This is a multi-step process involving operations related to cleaning the data, creating feature vectors from the reviews, visualizing and evaluating the quality of the features, performing topic modeling, clustering reviews into topics, and finally visualizing the clusters. Let's look at some of the relevant challenges in the context of this example. The first challenge we discuss is the lack of an integrated analysis environment. Text analysis workflows often require users to employ many disjointed tools such as spreadsheets for data preparation, computational notebooks for model building and evaluation, and visualization tools or libraries for exploration. We call these visual interactive text analysis, or VITA for short. Now, moving back and forth between these different tools while iterating over various steps can be cumbersome and overwhelming for users. The next challenge is the difficulty in implementing the workflows. As shown in the example, these workflows often involve a wide range of operations. Many of these operations are custom built. For example, operations like stripping HTML tags and removing URLs are frequently used in cleaning web documents. But sharing and reusing these operations across projects can be difficult. Therefore, users are forced to write these operations from scratch or copy them from previous projects. Finally, Vita workflows require systems to be both interactive and expressive. However, the disconnect between various tools creates a lack of interactivity between data and their visual representations. While scripts or codes are expressive, they are often not interactive. On the other hand, visualization tools are often interactive, but they lack the expressivity of scripts. Let's see how Leam attempts to address these challenges. Leam is designed to be a one-stop solution for visual interactive text analysis, or VITA. It leverages several design considerations distilled from existing work and our own experiences working in an industrial research lab setting. Leam integrates three paradigms: spreadsheets, computational notebooks, and visualization tools into a single system. As shown here, Leam's user interface contains four components. With operator view, users can perform various operations via button clicks. The visualization view displays the user-created interactive visualization. The table view not only displays the raw data, but also allows users to operate on it directly. Notebook view lets users compose and run text analysis workflows via Python scripts. So using these components, users don't need to use multiple tools, and they can actually perform text analysis in place. Moving on to the next challenge of authoring diverse Vita workflows. Now let's go back to our example Vita workflow involving various steps. Many of these steps or operations are repeated across projects. So how can we automate the process of creating, sharing, and reusing these operations? To do so, we introduce a visual text algebra, VTA. VTA formalizes the domain of VTA operation and abstracts these operations into high-level operators. Here, we see the domain of VTA, which contains primitive data types as well as composite ones like text and visualizations. The four types of high-level VTA operators are selection, transformation, composition, and coordination. I'm not going into the details of these operators for the purpose of time. However, we show an example of the coordination operator later. VTA operators are specified in JSON format. For example, the JSON specification shown here is for a TF-IDF operator. The operator takes a list of text reviews as input and returns a list of corresponding TF-IDF vectors. Users need to also specify other parameters related to storage and presentation of the output, which we don't cover here. We refer the viewers to the paper for more detail. Now, let's see how Leam manages interactivity and expressivity. The JSON-based VTA specification can be quite cumbersome to write. Also, it's different from the typical script-based analysis workflows. So we developed Vital, which is a Python library that helps users issue VTA operators via scripts. However, they can also issue these operators interactively from the operator view. Both Vital and menu operators are translated to the VTA JSON specification in the backend for execution. Let's see some other examples of interactivity. Users can use the coordination operator to connect different views of Leam. Again, going back to our example use case of review analysis, let's assume the user wants to view the top ranked words by their TF-IDF scores in the corpus. The figure on the left shows how to link a bar chart with the reviews in the table view. Clicking a bar, which represents a top ranking word in the review corpus, will filter relevant reviews in the table view. So this enables users to interactively explore and evaluate the featureization operators. Similarly, users can specify multiple visualizations to be linked as shown in the figure on the right. Here, clicking in the bar highlights both relevant points in the scatter plot and reviews in the table view. So what's the current system architecture of Leam? The underlying data structure is a customized in-memory data frame called VitaFrame. We developed VitaFrame as a wrapper around the pandas data frame. The table view essentially displays the VitaFrame and enables VTA operations on the data. Leam's backend features a compiler for translating the VTA commands that the execution engine runs. A session manager manages data, code, and visualizations used in the current analytics session. To manage the execution of notebook view commands, the session manager uses a task queue. Again, to manage the interactions among views, the session manager utilizes a coordination graph to propagate user actions among linked views. We have already talked about the user interface where users can perform various operations. Finally, one point to note is that the development of a version control DBMS is still a to-do. So let's discuss a few relevant research directions. Since Leam's current implementation is main memory based, an immediate challenge is to enable efficient storage and computation on large datasets. One approach can be to employ the VitaFrame as a wrapper around data frame systems like Modin. Modin supports parallel execution of operators to ensure scalability. Because Vita workflows are iterative, versioning the Vita sessions involving data, code, and visualizations is crucial for ensuring reproducibility and provenance of user actions. However, there is a trade-off between fine-grained and coarse-grained version control. Finally, the current version of VTA only implements a subset of existing text analytics operations. So, we can implement more useful text analysis operators to increase VTA coverage. So as you can see with Leam, we have barely scratched the surface and there are several exciting research opportunities to improve storage, computation, versioning, and enhancing the coverage of VTA. Addressing these problems require interdisciplinary research efforts from the DB, NLP, HCI, and Griggs communities. So that's all about Leam. Please feel free to reach out to us with any questions or suggestions. I'm happy to answer your questions now.